Okay, so now we are going to study particle in 1D box. So as I said that time independent Schrodinger equation solution will change with respect to the problem. So this is the one problem. Okay, in this the potential is defined and we will find out the energy eigenvalues of the Hamiltonian and the eigenfunctions of the Hamiltonian. So let's draw the 1D potential. This is 1D infinite. It's a one particle in 1D box, or sometimes it is written in 1D infinite potential. Okay. It is 1D infinite potential. So you can write it in the bracket. It means that we know that a particle is inside this box, but we don't know where is it. Okay, where it is, that we don't know. So I am just drawing a particle here, but I don't know that if the particle is here only. The mass of the particle is m. Potential inside the box is equal to 0. Potential outside is equal to infinity. That is why this is called infinite potential problem or infinite box. Now, what do we mean when we say that this potential is infinity? Generally, we imagine that there are these big walls and a particle is inside those two walls in 1D potential, and these walls are infinite. But actually, what do we mean? Like physically, what it is? Physically, here potential is infinity means potential energy is infinity. Here potential means potential energy is infinity, and potential energy is infinity means here force is infinite, because potential energy arises due to the force only, right? So, and it is positive potential energy now, because it is positive infinity. This is also positive infinity, and always what positive potential energy mean? Positive potential energy means repulsive force, right? That's why you see that gravitational force is attractive force, so potential energy is always negative, right? And if a force is repulsive, then potential energy will be positive. If the force is attractive, then potential energy will be negative. You can write it down if you want. Here, infinite repulsion is working on this particle, this m mass particle. There are infinite repulsive forces are working, so that's why this particle cannot move outside of this. Physically, that's what it means. You can consider anything there, that infinite repulsive forces are working. And if the forces are infinite, then obviously the particle cannot go in that region. So we define this potential energy Vx is equal to, it is 0 when 0 to L, when x is greater than 0 and less than L, and it is infinity when x is less than or equal to 0, or when x is greater than or equal to L, because x is equal to 0 here and x is equal to L, because a single coordinate is here, because it is a 1D problem. Okay, that's it. Now we are going to solve time independent Schrodinger equations, but our motto is to find out the wave function, right? So one thing we already know, that because the repulsive infinite repulsive forces are working outside this box, then particle cannot be found there, at least that is we are sure, right? So if particle cannot be found there, means the wave function or the probability of finding the particle outside is 0. If the probability is 0, means the wave function also has to be 0 there. It means that the wave function outside, in the outside regions, it is 0. So for x is less than 0 or x is greater than L, the wave function is already 0. So that is already solved. We do not have to solve in this region. So outside the box, okay. Now inside the box. In this region 0 to L. So inside the region we can say 0, 0 x. Just a minute. Okay, so in this region we are going to solve the Schrodinger equation, because in this region we don't know about the particle where it is and what is the probability. So we will write the Schrodinger equation minus h cross square by 2m d square by dx square, and that wave function we are writing as psi x, that we have represented as xx, now we are writing as psi x, same thing, and that plus Vx. What is Vx inside? 0. So we'll put 0. So that is equal to E psi x. That is TISE, time independent Schrodinger equation. Now this equation you can easily solve, because this is not partial differential equation, this is ordinary differential equation, so you can solve it by d square psi x is equal to minus 2m e upon h cross square psi x you can bring this part in that side and it becomes 2me upon h cross square. This equation might be familiar to you. How do we solve this equation? We write d by dx. This is second order differential equation, right? So the solution of this is equal to Cf plus Pi. You might have seen, right? So d by dx we represent as capital D. So d square by dx square will be written as d square. So d square, it will become d square plus 2me upon h cross square, right? So here we will write one thing also, that k square is equal to 2me upon h cross square, in order to simplify it. So it will become k square equal to 0. We will remove this psi x from here. That is the method of solving this equation. We will write like this and we will remove this psi x. We will just equate this thing equal to 0. Okay, and we will solve for d. So d will give you minus k square, right? And then plus minus iota k. Now solution of this equation is written in two ways. One way is this, and one you can get from the another. So solution of this means solution means this psi x is the solution. Solution. Because see here, after writing this psi x outside of the bracket, there is nothing in the right hand side, it is 0. So the solution just becomes CF only. Pi is 0. Okay, this CF means complementary function. Pi means particular integral. You do not have to remember it. Just remember CF here because there is nothing in the right hand side. It is 0. So solution is only CF, and that CF is written like this. That one coefficient is there. We say C1 dash, or you can say C1 e to the power iota kx plus C2 to the power minus iota kx. Because there are two roots here, na? Plus iota k and minus iota k. Both of them we are going to write in the exponentiation, writing these two coefficients also. So we know that if the differential equation is second order, then there will be two arbitrary constants always. Right? Whenever the equation is second order, then there are two arbitrary constants C1, C2. So this is one way. Now if you write this e to the power iota kx as cos kx iota sin kx, this identity you know, e to the power minus iota kx you can write as, this is one identity, so you need to remember it. If you use this in those in that above equation, you get this wave function. You can write it as, let's say, a sin kx plus b cos kx. Again, there are two arbitrary constants. So it is a rule that if you solve a second order differential equation, then there will be two arbitrary constants. If it is a single order differential equation, there is a one arbitrary constant. Now how we remove these arbitrary constants? Because the solution is not complete yet, yeah, right? Because a and b can be anything. So the solution is not complete. So in order to find out a and b, we use boundary conditions. Okay, mathematically, in order to remove the coefficients, we use boundary conditions. And physically, if you look into physics, then we know that we have defined this solution, but it is not fixed because we haven't put the information here that where are the boundaries of that infinite potential. Have we put that information here? No. So how would this equation know that the boundaries are at x is equal to 0 and x is equal to L? That information we have to feed, right? Then only we will get to know the complete solution. Otherwise, this solution will be the same as this solution because we haven't put the information. So we will feed that information. So this a and b will be removed. So we are going to use boundary conditions here. That is going to be our work every time. Every time we will solve the equation first, and then we are going to exploit boundary conditions in order to remove the coefficients. Okay. And these boundary conditions will tell you also that where the wave function has to become 0, right? Physicality, in order to bring the physicality into the problem. For example, we already know that outside here wave function is 0, outside region. Inside we don't know, but we know that wave function has to be continuous. So here also wave function has to be 0, because here it is 0, so it cannot suddenly have some value from 0, right? It has to be continuous, so it also has to be 0 here. So these kind of conditions we are going to put. So the first boundary condition tells you that psi at x is equal to 0 has to be equal to 0. Okay, and the second boundary condition, this is the first boundary condition, the second boundary condition will tell you that psi at x is equal to L also has to be 0 in the same way. And you can see this by one thing also, that because here also the potential is infinite at this point, so particle cannot be found at this one single point, it has to be 0 at this point also, x is equal to L also. So let's put this condition, first put this first condition. So psi x is equal to 0 is a sine 0 plus b cos 0, and the total has to be equal to 0. So sine 0 is 0, so 0 multiplied by a is 0, b cos 0 is 1. So from here we get this, b is equal to 0. So one coefficient we have found here. Now we will put that coefficient in the above equation here. So we get psi x is equal to a sine kx only, because b is 0. Now the second boundary condition we are going to use, that psi at x is equal to L, it becomes a sine kl also equal to 0. Now you know that a cannot be 0 here, just as you said, no, b is 0 there, a cannot be 0. Why? Because we have already said that b is 0, and if we will say that a is also 0, means that the total wave function will become 0 from here, because the total wave function is written from here, no? So a is also 0, b is also 0, so then it will say that the probability of finding the particle inside the box is 0, but that is not possible, because particle is there, we have put the particle inside the box, we don't know where it is, but that is there, and how it can escape when the infinite repulsive forces are working. So a cannot be 0. So what is 0? And when sine kl is 0, then what can be the value of kl? N pi, because for these values only sine becomes 0, where n can be 1, 2, 3, 4, 5, like this. And I do not write equal to 0, n is not equal to 0. Why? Because if I put n equal to 0, again the same thing. If I will put n is equal to 0, then this k will become 0, right? And if this k will become 0, then the whole wave function will become 0. No? There is one reason also, that also I'll tell you. That is the main reason. K here cannot be 0, because when we will write energy, okay, energy values, then that will include K. And if K will become 0, then energy will also become 0. And 0 energy is not possible in quantum mechanics. Even when the particle is in the ground state, it has to have some energy. It cannot be 0. Okay, so that's why n cannot be 0. Okay. So by the way, this will not become 0 if k will become 0, because this one will become 0, k is 0, then cos 0 is 1, so it will just give you b, so that is not 0. So from here we can at least write the value of k, n pi by f. We will put that in the wave function psi x. it will be a sine n pi x by l, where n values are 1, 2. Now you can see that k is equal to n pi by l. Na? So here we have written k square is equal to 2me upon h cross square. So let's equate both of these values. K square we have written there, na? Equate with this 2me upon h cross square. So k square here means n square pi square by l square, and that is equal to 2me upon h cross square. So E will become, instead of E I write En, because it depends on some value n now, right? So En is equal to n square pi square h cross square divided by 2mh square. N value is 1, 2, 3, like this. So here you can see that if n becomes 0, energy becomes 0, which is not possible in quantum mechanics. So we got the energy eigenvalues, we already got here, right? Energy eigenvalues for n is equal to 1, it will become pi square h cross square divided by 2m square, like this. Now this wave function, in this wave function only a is left, which is unknown. All the other quantities are already calculated. So we will normalize it, because as I said that every function, every wave function has to be normalized, right? Normalization means that total probability psi star psi dx in the whole space should become 1, and that is true because particle will be somewhere, right? So the total probability should sum up to 1. In the whole space. So then only the wave function will be acceptable. Or you can write it like this: psi mod square dx also is equal to 1. That is the normalization condition. So we will apply this normalization condition on this also. So it will be a square sine square and pi x by l dx. Now from minus infinity to infinity you can integrate it, but you know that the wave function is 0 in this range. It is already 0 in this range, right? And it is already 0 in this range, so the integration will automatically give you 0 for these reasons. So only you need to integrate from 0 to L, because that is finite only. Because that wave function that we have written, that is also for that reason only. We have written the limits now. So from 0 to L, and you will write it equal to 1. Now this is the integration, so that you are going to solve. Can anybody tell me that how to solve this integration? Obviously we are not going to spend time solving this integration, just the method you tell me. How to solve this integration? Okay, I got one answer. Cos 2x, very good. Very good. So you will use half angle formula, cos 2x formula, right? So like cos 2 theta is equal to 1 minus 2 sine square theta. So you will write the sine square theta and all the other things you will write in one side, and then those things you will integrate. cos 2 theta. Another formula is also there, 2 cos square theta, half angle formula. If you use this formula and you calculate the value of a, that will be equal to root 2 by l. Now we get our wave function psi x is equal to, that also depends on n, so I am putting this n subscript here. This is the wave function, or this is the eigenfunction of Hamiltonian. So the problem is solved. And the energy eigenvalue also we have written as n square pi square h cross square divided by 2 square. Okay. So here, as you can see, one thing that there are some specific energy levels only which are possible for the particle, right? Otherwise, if you think classically, then a particle can have any energy, right? Because it is inside this box, so it can have any energy. If it can have 1 joule, then it can have 1.1 joule also, right? Classically, what restrict it? Nothing. But quantum mechanically, we see that what is the reality. Quantum mechanically means really what is happening, that some of the specific energies are possible for this particle only, because it is Hamiltonian's eigenvalue. So this tells you all the possible outcomes of measurement of energy operator. So each and every time if you will measure the energy of that particle, you will get these values only. You will not get any value between these two values. So that is why it is called quantum mechanics, because the energy levels are quantized. Okay, some of the specific energy only a particle can have. So ground state energy, if you want, right? Then n is equal to 1 will give you the ground state energy, because n tells you the level. Okay, because energy is increasing with respect to n here. So E1 will give you the ground state energy, which is pi square h cross square divided by 2ml square. So even the ground state energy is not zero here. Then you can write first excited state. And what is the ground state wave function? That is psi1 is equal to root 2 by L sine pi x by L, because n is 1. Now if you want to draw it, if you want to draw this ground state wave function, how would we draw? This is the infinite potential. It becomes like this if you will draw it. So here it is x is equal to 0, here x is equal to 1. So because this do not cross this line, it means node is 0. Number of crossing this line is defined as number of nodes. So here you can say node is 0. That is the wave function only, psi x. But what is important for us? Psi x mod square, which tells you about the probability. So let's draw that as well. So square of this will also be in the same shape, but it will be at some higher height. Okay, the height will be longer, so it becomes like this. For this reason only, you can check that by putting the values of x and x is equal to 0 and anything between 0 and l. You will get this type of waveform only. You can check that by putting here, not now, at home. Now let's see the first excited state. So it means either the charge, either that particle have that energy, ground state energy, or it will be in first excited state means just the energy greater than that. So that will be E2. That will be 2 square means 4 pi square h cross square divided by 2 ml square, and the wave function will become psi 2x root 2 by L, which is different from the previous one. So let's draw again the wave function and wave function mod square. Wave function this time you see that will be in this form. That is a sine form. Okay, because you can see here at x is equal to L by 2 it becomes 0. This, and at x is equal to L also it becomes 0 again. So this is x is equal to 0, x is equal to L, and this is L by 2 at midpoint. So here this time there is a node, there is one number of node because it is crossing this line. And if we draw the psi x mod square, so this is positive part, this is negative part, right? So if you will take square, then both of them will become positive, right? So it becomes like this, and the height will also be increased, or you can say the amplitude will be increased like this. Okay, this height is also a little bit bigger than that because it is square. So it means this psi x mod square gives you the probability of finding the particle. Means that if the particle is in first excited state, then you will never find the particle here at the midpoint, because the probability of finding the particle at the middle of the box is 0. Isn't it that strange, right? It's also strange that if a particle is moving with a little bit more energy, that is the first excited state, then you will never find the particle at the midpoint, because it might be moving from one place to the another, but you will not find the particle at the midpoint. That is kind of the strange thing. Okay. Then you can keep drawing like this for others, for other like psi second excited state also. You will see that the number of nodes will keep increasing. For this, if it is 1, for the next one it will become n is equal to 2. For example, like this, it will become like this. Okay, that this time there are 2 nodes. Like this. So you can see one thing also, that the wiggles are increasing here, the wiggles in the wave. In the first one it is no wiggle, simple like this. Now there is more oscillation here, no? More wiggling is here. Here even more wiggling is here. You will find that if you will keep going on the higher and higher excited state, it will become like this. It means that the energy is increasing more and more, right? Because see that this distance is fixed, and if more wiggles means more frequency means more energy. So things are connected here. We can check the orthogonality condition also for this. See, normalization we have to do, but orthogonality is already satisfied there because those are the eigenvectors of Hermitian operator. And you always remember that eigenvectors of Hermitian operators are orthogonal, right? Orthogonal means this 0 to L psi n star x psi m x dx is equal to del nm. Means del nm means the orthonormality it is. When I write del nm, that means it is orthonormal. So here you will see this is orthonormality. Because if it becomes 1, that tells you that the function is normalized. If it becomes 0 for different n and m, then it is orthogonal. So that's it. You can calculate for this is general, so we are writing it as minus infinity to infinity. And for this specific case, if you write 0 to L sine so see there is root 2 by L also multiplied both of the sides. So that will come outside, will become 2 by L. Root 2 by L into root 2 by L is 2 by L is equal to del nm. Means that 1 if n is equal to m and 0 if n is not equal to m. Now you can try calculating the expectation values in ground state, right? Expectation value of x you can find out in the ground state, expectation value of momentum you can find out in the ground state or first excited state, anything. How do we write the formula for the expectation value? Expectation value of a cap we write as psi star x a cap. If it is normalized, then this only. If it is not normalized, then you write this also, psi star x. So for any state you can calculate this expectation value also. Here you can see that the wave function is real, it's not complex, right? That's why the expectation value of momentum will become 0, as I told you before in the previous classes.